and here we go. All right, welcome back. We are Game 3001. That's Artificial Intelligence for Games at George Brown in the winter 2022 semester. And it's week 7, part 1 of our broadcast and recording. This is for the lecture. One thing we've changed this semester is that there are no exams for this particular course. I think the great thing about this is it provides us with the ability to spread out some of the content that we have, although we've kind of expanded on some of it as well. So adding a little bit more detail where we can. So so that's the kind of stuff that we've been talking about all semester. Trying to spread things out a little bit. But let's talk about what we did last week. Last week we talked about during our lecture division schemes, how to make your pathfinding real. Like take the idea, the concepts that we were talking about for A-star and for Dijkstra, and then actually kind of coming up with a division scheme. A division scheme is a way of separating your world into bits, little components we call nodes and connections. And what we did was we talked about several kinds of, or three different types of division schemes. We talked about tile-based graphs, which is what we're doing, some kind of points of visibility, and I gave you guys a bit of a short demo with Unity on navigation meshes. Now, building a navigation mesh in SDL, that would be a big challenge to do. It's not as easy as doing the other stuff. But again, if you were to do something like that, then I think it would pay off in terms of pathfinding, because once you've been able to use the geometry in the map, on a 2D map, in a 2D world, especially in an indoor environment where you have rooms, the navigation, using a navigation mesh to accomplish pathfinding is pretty cool because it gives you the division scheme that you need. Now, again, A-star can work on any one of these or other types of division schemes that are out there. But these are the most common ones that I've kind of mentioned here, with navigation mesh being the most common nowadays in 3D. So that we talked about. Last week during lab, we also added neighbor references to tiles. That's what we did last week. We also coded 2 heuristic functions, Manhattan distance and Euclidean distance, which is pretty cool. We found we were able to switch between them using IMGUI, and we call our tiles smart tiles because they actually give you the distance calculation based on the heuristic, the evaluation function that we're giving you, from each tile to the goal tile. When you move the goal, then the whole map recalculates, right? That's what we've given you so far. And that's a great advantage because now you have at least the structure that you need to start doing that finding the shortest path functionality. Okay, so I mean, we've taken you most of the way there to start. After this week's lab, you should have everything you need to complete your assignment 2. Okay, because we basically explained everything from one lab to the other. If you've missed a lab, like some people have missed labs last week and so on, remember that each lab portion or component is worth 4% of your final grade. So it's not a small amount. Let's get into this part. So this week we're improving on A-star. How do we improve on it? And again, we'll talk a bit of theory on hierarchical pathfinding. We'll also revisit A-star again and talk about it, the algorithm a little bit more. We're going to incorporate this algorithm this week into our lab. We're also going to talk about a few A-star variants and other heuristics that can also help us, kind of mix and match to create a good solution for our tiles. One thing I also shared with you last week during lab, for those people who had me during lab, was we also had a little grid of tiles that I kind of used with you guys, and I shared that last week on up on Blackboard. But basically, we talked about a good way of calculating things using some kind of grid system. So for those people who haven't seen this, because you're a part of Alex's lab, it's totally fine. But basically, what we said was we talked about 2 heuristics. One of them was Manhattan distance, that is kind of going around a building like this. And I kind of shared this Excel spreadsheet with you to kind of calculate stuff. And the other one was Euclidean distance. And the difference between a Manhattan and Euclidean is it would kind of go down here and then it would step down, step down, step down. It would do this step algorithm, and I kind of talked about this with you. The distance in terms of tile count is the exact same because we're using um, tiles that are, you're not allowed to travel diagonal. You can't go this way across tiles in the assignment that we've given you. You can only use a 4-directional movement, so up, down, left, and right. And this proposes or presents some additional challenges for you in terms of finding the shortest path because you're just marching along, from one tile to the other, top, right, bottom, and left in that right winding order. One thing we also found was what happens when you get to this? How do you break a tie between going to the right or the bottom? And our tie breaking technique is the way we order the tiles. And we're going to see how when we build our build or find shortest path algorithm, that what I do is I build an array of tiles that are neighbor tiles, right? So we look at our neighbor tiles. We already have an array, 4 tiles, and we start counting from the top, right, bottom, and left. And we've kind of arranged all the neighbor tiles in that order already. And all you need to do is basically check, is this one the smallest distance? If not, then go to this one. Is this one the smallest distance? No. If not, then go to this one. And keep checking all the tiles until you find the path that has the smallest distance, right? Now, if these two paths are the same, or if these two paths are the same, you go to the, you use the winding order that we talked about before, which is top, right, bottom, left, similar to the box model on web programming. So in this case, that's why you can see the green path goes this way and down, right? Because this right here is the shortest distance, right? When it comes to Manhattan distance, right? You're going to go this way. But what ends up happening is when you're here for Euclidean distance, this is actually up here. This is actually a more expensive tile than this one. And that's why you would go down this way, right? Because this one, there is no tie in this case with Euclidean distance. Both algorithms, although they have, which we talked about last week, both heuristics, which is just estimation costs, where we've removed the tile costs from the equation because the tile costs we said were 1, so equal tile costs, so that way we don't have to worry about difficult terrain or crossing over a river or anything like that. They're all the same. Let's say you're going over a field and it's the exact same characteristics of the terrain. If that's true, then they're exactly the same. The problem is, what happens if we have some kind of block? And we're going to talk about this. Example, let's say I have a wall that goes here, right, to the goal. Now, which one is the most effective and what's the tile cost? And that's the stuff we're going to kind of go through today as I do some more examples with you in lecture. Okay, so that we're going to talk about this. We're going to use this graph. So for those of you who don't have this, please go to the previous lectures notes. So if you go up to Blackboard, and if you go to content for week 6, okay, the content for week 6, I'm going to use this example. Please pull down the grid system Excel spreadsheet, all right, so you can practice along with me, so you understand. And why do we care about practicing? So that way, when you troubleshoot, when you do debugging, you can say, wait a minute, what happened just there? Did my autonomous agent do what I expected them to do? And if they didn't, why didn't they? As an example, why is that possible for the autonomous agent to get stuck? What's the termination condition that's going to terminate me out of, push me out of continuous pathfinding, right? Because there's going to be a limit, as an example, right? So we'll talk about that in a bit. So that is week 7. Week 7 is where we're having our thing, but week 6 is where we have this thing, which we're going to be talking about later. So please pull this up and we'll talk about it in a bit. All right, so that is where we're starting. We're starting with how do I improve A-star, right? Because A-star's got some issues. We're also going to be talking about hierarchical pathfinding. So what if I can break my world down into chunks? Actually, I'm working on my master's thesis right now, which is breaking a long password that's 20 characters into chunks for memorization purposes. And it seems that breaking stuff down into smaller pieces, right, is the right way to go. So I want you to think about this for a second. That goes with that whole philosophy of, you can't eat an elephant, and a whole. You can't do that. You got to cut it up into smaller pieces to eat it. And I know this is kind of, it sounds like common sense. And why the elephant? This is just part of the philosophy. But the idea here is that it's impossible, right? You can't just try and figure things out in one big blow. And that's how programming works best. You kind of sit there and say, what's my problem I need to solve? And this is the problem I'm solving. I'm solving pathfinding, or I'm solving some kind of movement issue that I'm trying to solve. So how can I take that problem and make it smaller and smaller and smaller, and break it down into small reusable chunks when it comes to programming that I can, kind of use later on. That's the idea behind it. And the problem that junior programmers have is they don't know where to start. This is a very common problem. So don't be dismayed if that's you. They don't know how to break stuff down into smaller chunks, right? Because they don't know where to start. And sometimes what they're worried about is, my code sucks. My code is terrible. I'm terrible at coding. It's kind of like brute force code and stuff. And remember, my philosophy for you guys that I'm sharing with you all the time is, don't worry about brute force code right now, right? When you're coding. Again, you're in your second semester at George Brown, and you're doing some very difficult programming at the same time, right? So for me, it's more about, make it work. Make it work. Do whatever you have to do to make that thing work, right? And then refactor. Those are the two parts to it. Make it work, and then refactor. Go through your code and make it better, right? Because we even have some stuff in lab that we've left that needs to be improved, and we're going to be doing some of that this week with some code improvements, because it's too crazy, the stuff that we've got in there. For example, that offset that we keep on adding, that can be improved. We can remove that and put it somewhere globally, reduce some of our code, and it's going to help us. The other thing that we could also do with this, and some people have mentioned this in lab, is, why don't we make a grid class? Why don't we do that? So there's a lot of things you can do, and we'll get to some of those. And sometimes we can't. We just move on, because we have a time limit. Like everything that you do has a time limit of what you have to kind of accomplish. So hierarchical pathfinding, breaking things down into chunks. A-star pathfinding revisited. We're going to go through the algorithm one more time. I'm also going to look at other heuristics and variants, and stuff that's due this week. Lab 5, individual, due Sunday at midnight. That's what it's due right now. Assignment 2, which is your group assignment, is due also on Sunday at midnight. That's the last day of the first half of the semester. Again, if you haven't, for whatever reason, done this, and I've reminded everybody a bunch of times, you will not be able to do any of your assignments unless you join a group. On that, I've also released 2 more assignments, assignment 3 and 4. And I know people are saying, this is overkill now. Oh my God, we have so many things due, Tom, and you're releasing assignment 3 and 4. Yes, I'm releasing them early because I want you to understand that assignment 3, 4, and 5 is also another one. 5 takes the place of your final exam. It is a presentation that you're going to present your game that you're making for assignment 3 and 4. So you're making a small little game, which we'll talk about in a few minutes. All right, so let's take a look where we are. We're sitting here at week 7, again, at the bottom of the first half of semester. And we're just wrapping up a pathfinding this week. Okay, that's what's happening. And this week in lab, we're going to talk about finding the shortest path, creating a finding shortest path method, displaying the path list, as an example, creating some kind of spawn object method that allows us to generate random obstacles to test our pathfinding. That's what we're going to do this week, to kind of stress test it as much as possible. And that is this week. But what's happening in the coming weeks? So when we come back from break, one thing that we're going to start talking about is decision making. And we have brand new structures that we're going to be working with together. We're going to be working with using decision trees and creating decision trees and what those things are. We're going to be getting into state machines. You guys have been working with states right now. I got a question from Nicholas saying, is the second half supposed to be in person? And no, it's not. It was supposed to be in person, but we've decided to go full online until the end of this semester. I know the summer semester, if you're taking the summer semester at all, or anything in the summer semester, they're planning to go to a hybrid model for the summer, which is the spring summer semester starting at the end of April and May timeframe. We're going to continue to do this hybrid model, as COVID wanes. Hopefully it'll go away more, enough that we'll be able to be in person and people will feel more comfortable with it. Again, I've done in-person teaching already. And I'll tell you that it for both people, the professor and the student, it's a bit of a paradigm shift when you see someone, physically in the class and being physically in school. It's a little bit uncomfortable at the beginning because you're like, whoa, this is pretty crazy. I can't believe I'm physically here, you know. But it will come, and it'll become easier and easier as we do it. So yeah, September. Are we going to be fully online in September or fully in person? I don't know. It really depends on so many factors. Is there going to be another wave? I really hope not. Um, is there going to be are there going to be other extraneous factors that are going to prevent us from being in person? Are we going to maintain the hybrid model until then? I don't know. But as far as I know, at least by the summer, so far the plan is to go hybrid. That means 1 day a week, or half the time, for your lectures, you're online, and the other half for your labs, you're in person. That's the way we're going. We're starting in the summer, and that means that it'll probably carry forward until the fall if that model works. All right, but let's continue with this. So we're talking about, we're in week 9. We're talking about week 9, and that's where we're starting decision making, state machines, which you're learning some about right now in fundamentals, behavior trees, which is kind of, as we march forward from one week to the other, it builds. You can see that we also have labs that are worth 8%. So lab 6, which is, starting in week 9 and ending in week 10, that'll be worth 8% compared to, let's say, other labs. Lab 7 is also a big one. Lab 7, because we start building the tree node class and so on, and we work from lab 7 until we get to, actually, that's a really big one. That's like a 3-part lab, 1, 2, 3, as an example. So that's like worth 12% of your final grade, which is almost like an assignment in itself, right? If you think about it. So that's why it's like Alex and I keep telling you, it's super important to attend your labs, and so on. No assignment after we're done this week. There's no more pathfinding. It's all about decision making, and decision making. Remember, I kind of talked about this earlier. This course is tough, but it starts easy and it goes. Actually, let me take that back. It starts semi-challenging, right, with kind of steering behaviors. Then it becomes challenging with pathfinding, and then it becomes harder with decision making until we've covered most of the stuff in AI. So yeah, no more pathfinding after, like, not exactly the same way we're doing it after this week. So again, we're going into this, and you can see that we're talking about tactical and strategic AI in week 14. And you can see that assignment 3 is due at the end of week 11. So it's, we're sitting at week 7, so 4 weeks from now. And assignment 4 is due at, kind of in the week of April 11th. I think it's April 17th, Sunday of April 17th, that we're going to be there. And then finally, the final week of class, as an example, there will be no lab for this one. It's just going to be presentations. So there won't be a physical lab for week 15. There'll be presentations the entire week, both in lab and lecture hour. All right, so that's what's happening. And the presentations that we're going to be doing are based on your all the stuff that you're doing for assignment 3 and 4. Okay, so that's really the end of, or that's the second half of semester I wanted to talk about. We do a little bit of machine learning in the last week just to spice things up a little bit and for enrichment. But we don't actually do an example with Q-learning or reinforcement learning, which is awesome. I think it'll lead you nicely into a more advanced course in AI if you ever want to, kind of pursue something like that in the future. All right, so that is the plan for the second half of semester. One thing I also want to talk about is where we sit from a marks perspective at this point. So by the end of the first half, if you think about it, we've got 25% of your marks are going to be group. Again, we're kind of sitting right here. And then you've had several labs. We're sitting right now at lab 5. Lab 1 was kind of an individual lab, so 4%. Lab 5 is an individual lab, which is worth 4%. And lab 2 was basically 2 labs. They're worth 4% each. and lab 3 was 2 labs worth 4% each. So really we've had 7 labs, right, worth 4% each, and that's 7 out of 13. We're only going to look at the best 11, right? So again, we're about halfway when it comes to the number of labs we're doing for this semester. So right now, if you think about that, that means you could have 28% individual plus another 25% group. So you'll have a very good understanding by the end of this week, where we hope to get all your marks uploaded to Blackboard, where you stand in this course, which is the most important piece. Okay, so that's what's happening, just a bit of a course update. The other thing I wanted to talk about as well is that labs, again, another reminder to be completed individually. I've run into some labs where people, for whatever reason, say, yes, I'm working with me and my lab partner on this lab. No, there are no lab partners, okay? You have assignment partners, but there are no lab partners. You work individually. If you submit something with your lab partner, you and that partner will get 0. Just letting you know. So, and the other thing people keep asking about is, can I get an extension on my lab? The answer is no. The labs are due on Sunday, and they're supposed to be in person, right? That means that when we get together on Thursday, that is your opportunity to get the lab done with myself or Alex, get it done, get it submitted, and you're good to go. For the most part, the only thing you need to do is put together your little video and your lab report, which we supply for you. So you just have to go through it, and it takes you maybe, if you're optimal, 10 or 15 minutes to get done, maybe another take or two, and you're good to go if you follow it along. Really, all it is attending class, following along, asking the questions as much as possible, and then if you have a problem, meet with your professor. All right, so that is what we're talking about. Let me just briefly talk about assignment 3 and 4. We're going to get back to this again and talk about it in more detail in a bit. But I want to talk about them, introduce them, and record them so you can always go back and look at these recordings later. Let's talk about assignment 3 and 4. So assignment 3 is all around decision making, and so is assignment 4. And for this assignment, you may work alone or with one or more partners. I've made it so that the group size, again, is up to 3 people. Again, we're moving up, more challenging, even more. I'm not going to make it 2 because I think 2 for assignment 3 and 4 is very difficult. It'll be very, very difficult for you to complete it. Assignment 2, though, I think it's doable with 2 people. There's not a lot to do, but assignment 3 and 4, is only 3. So in this assignment, some criteria is marked as mandatory, which is what we talked about before. You need to use our assignment framework that we put up on Blackboard as a base to start off with. And your assignment must include a start scene, which is what we're giving you for 5 points for free with the start button like before. So all that regular stuff. Really, the start scene is just your getting going and for you to place your student ID and your name in there with your partners. That's really what it's for, right? Okay, here's something that's new. You must include a node class. So we've talked about nodes, but we made them into tiles for our division scheme here. But now we're going to actually do something that's a little different. We're going to create a node class, and you must create a collection of node pointers to enable iteration across all nodes. And this could be an STL vector, list, or other structure. So these are important things to note. You're going to have an appropriate actor sprite. This could be a spaceship, car, animated character, whatever you want. And the actor will be able to move in any direction by responding to key presses, example WASD, or by using the left stick on the gamepad and face in the direction of the mouse pointer, or by using the right stick on the gamepad, right? So these are the things that you'll be able to move. You're going to create an interesting map, and I keep on hearing, what is an interesting map, Tom? Make it your own. So think about this as a small little mini game that you're making. It's overlaid on top of the nodes, just like we have in our current example. We have a grid, we have tiles as nodes. You're going to overlay your interesting map on top. We're not going to be able to see the underlying, tiles or nodes unless we want to see them through a debug view. Again, this can be creative. You may use a tile map set. So this is not tiles, a tile class, but a tile map set, and you can use something like tiled or whatever. Or you may draw your map tiles individually. It's up to you. Your placing must include appropriate background music. So you're going to be tasked with some music too. Ensure that the volume is set to a reasonable level. Add simple sound effects and various actions or triggers in the placing. And this may include, but is not limited to, the actor moving across the map, firing a bullet. Please take a look at some of these extraneous things as well. for assignment 2. Assignment 2 also has some requirements for sound and so on. So please make sure you see this in assignment 2. You go through assignment 2 like I'm going through assignment 3, one thing at a time, right? So this assignment will set up all the key elements that will be reused in assignment 4. So this is kind of a foundation for assignment 4. And these include line of sight, which we're going to be working with for assignment 4, detection radius, player movement, which could be a mix of things like steering behaviors if you want, and enemy movement and others. Okay, you're going to have a debug view when you press the H key, or you can use keys when you bring up I'm GUI. So if it says press a key, remember always in our assignments, you're always allowed to swap out, press the H key for using I am GUI. Okay. So Simon's asking a question. Are you talking about assignment 2 assignment or assignment 3? The assignment we're doing right now that I'm talking about. 2. Let me get back to you on that. I'll explain that. But the short answer is the visual tiles for the tile map and the background tiles, which are the debug tiles we drew together in class, in lab, are 2 separate things. Okay, the visual tiles you have to make look nice, which remember, if you take a look at it, is you have to make a nice map. So that's something like an overlay on top of everything else. All right, debug view, debug keys, how to press them. You can also use I am GUI for this one. And you'll have to also include player animations and sound effects. This is why we're asking you to do 3 people. There's more requirement for this one. Where, again, you will show different kinds of animations depending on which way you're facing. Player combat capabilities. The player can engage in both close combat, melee, and range combat, shooting. For close combat, the player must be within an appropriate range, right? So close enough to the enemy. In order to register a hit. For ranged combat, the player will fire an appropriate fire and forget projectile in the direction they are facing. You guys should know about fire and forget type projectiles from your foundational classes you're taking, game fundamentals. And the player's orientation is set to follow the position of the mouse pointer or moving the right stick on the gamepad. It's up to you. Player health bar was required. Game status. So how far in the game, how many enemies have you killed, and so on. Obstacles. Your play scene will include at least 4 obstacles that will stop the player and the enemies from passing through them. Remember, we did 1 obstacle and you guys had some challenges. Now you'll have 4. The obstacles will also block enemy line of sight. However, they will not block enemy detection radius. So the enemy can still smell you, hear you, have you on its radar, whatever you want to call it, in order for them to detect where you are. You're making a base enemy class. The base enemy class will move patrol along a predetermined path of nodes around the map, and the base enemy game object will have a health property which will be displayed in a health bar similar to the player's health bar. Your base enemy animations and sound effects will also be present. Base enemy will have line of sight. Base enemy will have a detection radius. And of course, we're asking you to use a Git and GitHub for source control. So really, it's just getting you for the first time, for the first part, is to get your enemy patrolling, your player moving, stuff animating, sound effects there. So basically creating a foundation for part 2, which is assignment 4. Now, we've given you a lot of time for this, like 4 weeks to get it done. Now, it may not seem like a lot of time, but it really is. So it's on you after you stop with assignment 2. As soon as you guys have a chance with you and your partner, what you need to do is sign up for new teams. We've made new groups for assignment 3 and assignment 4. Please do not sign up for assignment 4 yet if you're not sure about your teams. Then you're going to sign up for assignment 3. So first start off with the A3 groups that I've created. I've created 40 of them, right? So to allow you to either do it on your own or with a set of people together. Okay, so that's what's happening there. And I wanted to also share with you kind of a preview of stuff as we go forward. I'm just keeping my time in mind here just to make sure we're good. I think we're still good with time. And I wanted to talk about this because there is, in my opinion, some great examples of some stuff that we have that we can show you. So here is a game that a previous student from kind of the previous cohort from you guys. So they're right now Herman He's allowed me to use this. His name is Herman Hum. He is a student in 3rd year last semester, so he's pretty good. He created this one, and we're going to just preview what Herman did for his assignment 3 and 4, and this is kind of a really great example of something that you might be able to do with you and your partners. So let's bring that up in a second, whenever that feels like launching. My Visual Studio is taking its sweet time. And that's not Herman's problem, that's my problem. So hopefully that'll launch at some point in the near future. It seems like, oh, there it is in another window. Ooh, okay, here it is. So how does this game play, and what does it do? And you'll see what at the end of the day, it's quite a challenging game that he's put together, and I think it's good. What I'll do is I'm going to share the build with you guys on Blackboard, so you can check it out and see if it meets all the requirements. He's got a bunch of requirements. Now, this is for both assignment 3 and 4, so it's not just about assignment 3. And I think it's a good opportunity for you guys to take a look at someone else's work that has been created, before this course. All right, so there we go. So we have our player. He's running around. We have enemies that come out, and you can see that the player can fight. And you guys can't hear the sounds. I'll turn up the sounds while I move around and die. But I'm gonna completely die here because I'm getting nailed. But you guys should be able to hear the sounds now. So you can see I have a kind of a, there we go. Let's try that again. I have a enemy that is a ranged enemy. I have an enemy that is a, oh boy. I have an enemy that is a melee enemy. We have destructible objects in the environment where you can have stuff that can blow up, right? And your job is to basically kill all of the items in the game world, all the enemies, before they escape, right? Because if you don't, oh boy, if you don't do it fast enough, then they'll come out of they will respawn if you don't kill them in time. If you don't kill all the enemies in time, then they will completely respawn. And see how this enemy runs away? So this enemy is running away because he's damaged, he's hurt. Oh, I'm gonna die soon. And oh god. But you can see how this works, right? So let's see if we can kill this guy. See how the ranged enemy is trying to run away, and you can see how as they do, oh boy, oh, the knight's really hard to beat. Oh yeah. So it's kind of a, how many enemies can you kill kind of thing before you die. And I'm not really that great at this game, but it's a great game to play. So don't be scared. So this was done in your semester, in your year, right? So this he was in your semester. He made it for our class for AI. So it's something that's possible, is all I'm saying. And he did it alone. He didn't have anybody helping him out. So Herman is on his own, and he made this assignment for AI. Now, do I expect you to do something like this? Well, obviously this was an A+, right? And I have to show you, kind of stuff that is, he's not cracked. He's awesome, this dude. And I think, respect to the guy who can kind of come up with this kind of stuff, which is awesome for me, right? So this is how I think about it. Let's take a look at practice equal to awesome. Okay. Let's take a look at some stuff for assignment 3 as well. So I want to talk about this a little bit to use this as an example before we move on. So stuff that you need to know is there's basically different cases. There's 3 different cases where you have obstacles in the world. I've kind of drawn this very simple map where you have these nodes. So blue is nodes. You have enemies that have which is your base enemy class. Your base enemy class is going to have a little health bar, and so too will your player. Here's your player. And one thing that they're going to have to know, the enemies, they're going to have 2 sensing criteria. One of them is line of sight, and the other one is a sensing radius. Okay, so line of sight, if you can draw a line between your enemy to your player with no obstacles in between, that's the conditions for line of sight. If you can't do that, and notice that both line of sight in this case and the sensing radius are red. There's no way that they're good. But what about this case where you have case number 2? Case number 1, you have line of sight false, radius false. What about case number 2? Line of sight is false because we can't draw a line between the base enemy, which is the red square, and the player, which is the red circle. It goes through an obstacle, right? That's where the base enemy is sitting on a node after they finish patrolling, and they can't see the player, but the player is within the sensing radius, so the enemy knows that they're there. Okay, that's case number 2. Case number 3 is where the enemy can see the player. There's no obstacle, but the player is not within the sensing radius. Okay, and case number 4 is, of course, where both are true. The enemy is close enough to see the player and the sensing radius is on. Those are the different kind of conditions you can find with different kinds of obstacles. Here, again, in the game world, we've said a minimum of 4 obstacles are required for your game. And we can use nodes, these kind of invisible positions in the game world, to traverse the game world. One thing that we've also said is that for assignment 3 and 4, remember, we do not expect you to make a grid of tiles. So they're not going to be limited. The enemy will not be limited to traversing a grid of tiles, but rather they will be required to find the player in different ways. So example here, Git and GitHub. You'll need that submission criteria for your video is required as normal, and we've given you a small rubric that we're going to be using for your lab report for assignment 3. Okay. All right, so that is assignment 3. Let's talk briefly then about assignment 4. And you saw the difference. Assignment 4 that I just showed you, so that's Herman's version that he came up with. It was the completed version. Assignment 3 is the base where all they do is patrol around. Here's assignment 4. So assignment 4 is all around AI behavior. And again, you may work alone or with a partner. So what happens between assignment 3 and 4? Let's say you're really unhappy with your partners from assignment 3 and you feel like doing assignment 4, the second part, on your own. Remember, what we can do is, if you worked on a code base with your partners from assignment 3, you are allowed to use that same code base to continue into assignment 4 on your own, just in case, for example, you're not happy. Or let's suppose you started assignment 3 and you finished it and you're happy with your work and you wanted to go with some other partner. You can kind of combine with them. And you can choose any of the assignment 3 that you worked on, either your assignment 3 or their assignment 3, and make your assignment 4 with that, your final version. So that's how it's going to work. Again, this one is due in April 17th. That's Sunday. That's the week 14 by midnight. So several weeks away, right? Again, we're sitting at week 7. So that's another 7 weeks away before we get to 7 calendar weeks before we get to week 14, almost at the end of semester. And what is the difference is, for this one, you must have a working assignment 3. You must have a working assignment 3. If you don't have a working assignment 3, well, again, that will be an issue. You won't be able to do assignment 4. So that's why these assignment 3 and 4 are linked together. It's almost like one big assignment that we've broken out into smaller chunks. Speaking of chunks. Christians asked, are these nodes completely random or what? Nope, they're not completely random. I've just put them there so you can see that and we'll talk about that more when we talk about assignment 3 in more details. So now the requirements are AI actions. So the first part is, hey, can I make a standard base enemy class? And now the enemy will have behaviors. Again, the second half is all around decision making and behaviors. So the enemy will be able to patrol, move to player, do a close combat attack, flee, move to line of sight, move to range, move behind cover, wait behind cover, and ranged attack. Notice that when we played Herman's game, the enemies would hide and run away. They're using flee as an example, like we said. When the enemy is hurt, they'll run away and they'll do the flee action. Okay, so that's kind of the condition. So these are all the AI actions you'll have to map for assignment 4. You'll have 2 types of loadouts, okay, for the enemies. Notice that in Herman's version, we had a ranged enemy and a close combat enemy, and then he also made a bonus enemy at the end that can do both. If you wait long enough, a bonus enemy, the knight, will come out. They can fire long distances like a crossbow, as well as, he's armored and he can attack you. So that is create a close combat enemy and a ranged combat enemy. Those are 2 different loadouts. and you have different actions, you'll have to make a destructible environment. You saw that in Herman's game, I was able to destroy the barrels and all that kind of stuff, and so were the enemies. Enemy will respawn if you can't within a random interval, and the new enemy can be of either type, loadout. So that means like whether it's a close combat or ranged enemy. If both enemies successfully flee, then 2 new enemies will respawn, and that's kind of a bad thing. And there is a winning condition. If you can defeat or kill both enemies, right, without them having a chance to flee, without them running away, then you will be transported to you actually have a label that pops up that says you win. Okay, that's kind of the way it works. All right, so that's kind of at a very high level what it works out to be. But basically what you have is different actions and then different conditions to trigger those actions. Okay, so the actions are important. So, patrol, again, this is from assignment 3. You're just going to include it. Move to player requires line of sight. These are the conditions. Move toward the player using a rival steering behavior. Notice we're actually getting you to use the steering behavior mechanism. Stop at close combat distance. Okay, what is that? What is close combat distance? You have to determine that. And then play the move animation and related sound effects. So you have to do all these things. That's worth 3 marks out of 100. And then for each action, you're going to have different requirements like this. So example, you're going to flee if you're down less than 50% of your health, I think it is, right? So the flee action is move away from the player, avoiding obstacles, and leave the scene. Play the move animation and related sound effects. Okay, so that's what the flee action does. Move to line of sight. Find the closest node to the player with line of sight. Use obstacle avoidance along the way, and use the steering behavior to move. Play the move animation and related sound effects. So again, all the same stuff, building on the things that you already know how to do. Move to range. So this is for a ranged combat assailant. Requires line of sight. Use a blend of separation and cohesion steering behaviors to maintain an appropriate distance from the player. Play the move animation and related sound effects. Move behind cover. Find the closest node to the player that does not have line of sight, right? And move there. Play the move animation and related sound effects. Wait behind cover. The enemy must be behind cover. That's the condition. And the enemy will wait for a random interval and then leave cover. And like I brought up that little map, just for a second, I'll bring that back up again so you understand what cover means. And then we'll go on to actually the lecture for today, right? I know there's a lot, and some of you won't absorb all of it or any of it, but the great thing is you know what's coming, right? So this way you'll have a chance to start thinking about it. So again, imagine if this is my player. Notice that he is in, let's say this is enemy 2. The enemy 2, if he is a close combat enemy, then what he has to do is move from node to node around the obstacle until he gets close enough to the player to attack. But let's suppose I attack enemy 2 and I do enough damage, then, or if I do any damage at all, then what they'll have to do is they will as an example, be forced to go behind cover. And going behind cover is where I do not have line of sight. So it's line of sight is going to work both ways. Line of sight from the enemy to the player, and line of sight from the player to the enemy, right? So those are important factors that we'll be considering in assignment 3 and 4. All right, so that's what's happening. Again, 2 types of loadouts, which will have its own behaviors. And here's the close combat enemy, where when they drop down below 25% of their health, they'll just try and leave. That's what they'll try and do. And the other one is the range combat enemy. When they get hit at all, they will move behind cover, right? Which is something that is a thing that they're going to be doing. So if the range combat enemy is hit, perform move behind cover, and then upon this, perform the wait behind cover action. If their health drops also below 25%, they'll also flee. So you can see how that works. We're using those kind of things. Destructible environment means that you'll have to make some obstacles will have, will be destructible. So it says, take the obstacle class from assignment 3 and name it destructible obstacle. And this class will include a health bar of its own and can be destroyed by taking hits from either the player or an enemy. Okay, so that's something that you're going to have. So a fully destructible environment. All right, any questions? Are these nodes? Okay, Christian says ignorance is bliss. I don't want to know until I got to do it. Okay, well, that would be, I'm just trying to help you plan, Christian. So that way, you understand what's coming, and by now, hopefully you'll have a good idea of who you'd like to work with, and who you've been working with in assignment 1 and 2. And that's the reason why we're sharing this with you. You have access to it. So it means you can start it anytime you want. I fully encourage you guys to start it as soon as possible. Any questions for assignment 3 and 4 that you can come up with before we move on into the second part of our lecture, which is that was just admin and kind of getting up to date with the course, since we're at the second half or just the bottom half of semester, right? So I just wanted to go into the second part right now, which is the lecture piece. All right. So one thing to note in games, we've talked about this before, we often want to find paths from one location to another, right? And we're not trying just to find the shortest distance. We also want to take into account time travel, right? Which is like time it takes. There's a nice little example here. If you guys go here, this is where I took some of this. If you want to check this out, there's a great website that this guy kind of comes up with. I'll share this with you, and I'll put the link up on Blackboard as well. And what he allows you to do is you can check out what pathfinding might look like if you move this to different pieces. So you can say, well, what if he's in this room, or what if he's in this room, or this room, or that room? What's the shortest path? And you can see that it always calculates the shortest path for you, depending on which part of the level you're in. Notice that what he's done is he's used a division scheme where he's separated different parts of the room out in different spots, right? So this is kind of interesting the way he's done it here. All right, so this is the link for it. I'm just going to pop this into your chat if you're interested in looking there. There's some great resources there for what this guy has done. And let me just send it to everybody, not just one person. Let me just do that again. Sorry about that, Aiden. There we go. And he talks about how to represent the map, which is kind of a division scheme. He uses that. And he goes into a lot of detail about what happens with doorways, what does he do, and all that kind of stuff, which is really great. He uses different algorithms. He talks about breadth first search, as well as Dijkstra's algorithm and A-star, right? So this is the stuff that he talks about. And he goes into a lot of detail about this. And he has little animations that he kind of show you what it looks like when it comes to breadth first search, right? So this is what he does there. Which is neat. And let me just show you. He talks about how it works in terms of the way the pathfinding thing works and how do you set up your algorithms. He makes some examples of algorithms that you can use, as well as gives you examples of how everything looks. So you can see that this is breadth first search compared to Dijkstra's, and you can see that the path that it takes, breadth first search doesn't really work great because it cuts right through. But where Dijkstra makes more sense, right? So if I was to move this around, right, as an example, let's say I move it around over here, you can see that this always finds the, kind of the minimum distance used on breadth first search, right? And where Dijkstra actually explores, explore the whole world to find the best path as much as possible. But again, with those limitations we talked about before, right? So kind of a cool way of doing it. He talks about different kinds of heuristics in here as well, and he shows Dijkstra's versus a greedy best first search, right? So he talks about how that would work, right? There's Dijkstra, how it explores the entire world. Dijkstra and the greedy best first search work exactly the same way. So again, if I was to you can actually draw your obstacles here in the world to try it out, and you can see that how it would work, right? And how the path automatically adjusts to the obstacles that you're drawing here, which is kind of neat, right? So we can start that animation off. And then there's, he draws different kinds of situations where he shows you that Dijkstra, it eventually finds a path. It's short, it's longer, it takes a lot longer. But in this case, it's actually better than what greedy best search first does, where it goes inside here, figures out there's no way around this, and goes around. All right, so that's kind of how that looks. Talks about A-star in here, which is a great little tutorial on how that works, and how it compares to from A-star to greedy best first to Dijkstra's algorithm and what they do differently, right? And what the outcome is. and more and more and more. I think there's some great resources here. And he's also written quite a bit more about pathfinding here, Amit's stuff. And I think it's really great because at least what it allows us to do is take a look at other people's work. One thing to do is if you're going to use any of the algorithms that are not shown in lab and you want to use them in your project, your assignment 1 or 2, or even in your labs, you need to, if it goes beyond the 10% limit, you need to talk to Alex, myself, to talk about anything that you want to use that that we haven't talked about. But he goes into a lot of detail about A-star and a bunch of stuff. Great little link, and I'll put that up on Blackboard later. And that's why I included it here. So we want to start thinking about improving A-star because A-star can have its issues, and we talked about them. It really depends on the kind of map that you've got out there. So again, you can have a very efficient algorithm, but what happens when you get into tens of thousands of nodes, right? As an example, and let's say, for example, in an MMO, you have a division scheme from MMO or a big strategy game, and you want to make it better. So you need some more optimizations. And one of the biggest problems is it can be extremely slow to do your pathfinding from one node to the other. And the other one is it might take a huge amount of memory, which might make the game unplayable, right? It'll slow your game down to a crawl. All right, so you want to make it so it's better than that. And we can think about different ways of doing it. There's 2 different ways that are mentioned here. One of them is something called hierarchical pathfinding, which we're going to talk about. And there's another one, which is dynamic pathfinding. I'm not going to talk about this one, but the performance on dynamic pathfinding is quite low, but the memory is better because it's done dynamically, like it says. Hierarchical is breaking the world down into chunks, and we'll talk about that in a second. So let's think about what hierarchical means. Hierarchical means there's a hierarchy, parent-child relationships, and those kind of things that we've talked about before, right? And basically, it plans a route from one part of the world to the other, or from the start to the goal node, pretty much how we do. So here's how it works, right? Basically, we get an overview of the route first. This is where we want to go. This is our goal. And then we start refining it as we go. So we go down into the weeds. Example would be, here's one. To get to the rear parking lot, as an example, we'll go down the stairs, out of the front lobby, and around the side of the building, right? And that's for kind of a high-level overview of the route, which is pretty close by, right? And we'll go through the office, or we'll do one of these. We'll go through the office, out the front of the fire door, and down the fire escape. That's another possible route if you're not too high up, as an example, right? For a longer route, though, think about real high level. I want to travel from here to London, right? Well, I can't go there in one stop. I've got to do several different stops, if you will. Or I have to use several different methods to travel there, right? So I'm going to go from the London office. I got to go to the airport first, catch a flight, and then get a cab when we land. That's a very high level view, an abstract view of how to get to the London office, as an example. Let's think about it for you, right? You want to go to, how do you travel to school if you're ever going to get there? And again, if we're in-person learning, you got to figure this out. But think about how Google Maps work in many ways. It's not just a GPS, but it tries to find the shortest path based on different driving conditions. That's what it's doing, right? So if I want to find a path, example, from George Brown, to your house, right? That's exactly what's happening. But that's a high-level view, right? High-level view. But what about finding a path from within your house? The first thing you might want to do is, okay, you're in your bedroom, and you're going to map a path from your bedroom to the front door. And if you have to collect other things along the way, like your backpack with your computer and blah, 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 that's additional things you need to do before you get out the front door. So now you're out the front door, and let's suppose you live in a house, not an apartment. So it's a detached house. You don't have anyone around. You don't have to go through hallways or anything else. You go to the front door, and from there, you have to find your way, the shortest way to get to the bus stop, or maybe you have a car. If you're a driver, you go to your car, and from your car or the bus stop, now you have to plot the route from there, the second part of your journey, to go from there to George Brown waterfront, right, where we are, right? Then you have to park your car, find the parking spot, and then from there take the shortest route again from the parking lot all the way to the George Brown, to the building, And then from the building, from the entrance to the building, find the shortest path from there all the way to the classroom, wherever that is. So you can see that there's many pieces to this whole thing. And one of the things that we have to talk about is it's complex. Okay, it's complex. And so again, we plan first. The first step is we plan a very, very high level route, an abstract route. Okay. And then we take the first step of that plan and find a route to complete it. And then so on down the level where we can actually move once we start going. Once we plan the route, then we know where we're going. So this is where, as an example, you know, we have an algorithm we're going to use. We have a pathfinding algorithm, and we're going to apply it, but we're going to cut up our world or our journey into several pieces in order for us to get there, right? So after the initial multi-level planning, where we start off at a very abstract level, I want to go to George Brown as an example, and I'm going to hop on the bus or take the car. I'm going to leave my house. This is the high level. I'm going to leave my house, go in the car, and drive to George Brown, park, and go to my go to the building and go to my class. That is like high level, okay? But then it's like lower level might be, okay, I'm in my house. How do I get out of there? I'm out of my house. Okay, from my house to the car, what's the shortest route? From the house to your home, maybe it's in an apartment building or a condo, and you're going to your bus stop, what's the shortest route? So there's different parts or components to this whole journey, right? So here's an example of when we arrive at the bottom of the stairs on our way to the parking lot, and from there to the London office, we plan our route through the lobby. So you see, do a shorter plan. When we arrive at our car, we then have completed the get to the car stage of our more abstract plan, and we can plan the drive to the airport stage. So each stage is something that we can break up into little piece parts. The plan at each level is pretty simple, right? We split the pathfinding problem over a long period of time, only doing the next bit when the current bit is complete. Okay, so again, breaking our problem down into chunks. To be able to pathfind at higher levels, we can still use A*, right? And all of its optimizations. But in order to support hierarchical pathfinding, we need to alter the graph data structure a little bit. And the reason for this is because we're doing things in a different way. Let's talk about nodes a little bit for pathfinding, hierarchical pathfinding. So this is done by grouping locations together to form clusters. So I've got, example, 4 different clusters in this little diagram right here. Let me just bring this diagram a little bit bigger so you can see the clusters a little better. You got 4 little clusters. You can see that we've zoomed in on one of the clusters, and each cluster, right, has its own nodes that are inside of it. So nodes within a group, and you can have groups within another larger cluster as well if you want to, depending on how crazy you want to go, right? And you can see that this part right here, so this part right here is the entire house, and then this part of the house has even more pathfinding that's inside of it. Okay, similar to what we saw earlier with that website I was showing you, right? And the reason why is because you want to be able to navigate around, this office. Let's suppose this is an office. Okay, so that's kind of how it works. So individual locations for a whole room, for example, can be regrouped together. There may be 50 navigation points in the room, but the higher level plans, they can be treated as one. So all of this is one node, right? That's the single node in terms of getting there, right? So we start off with a higher level plan and figure out basic locations where we want to go, okay? And then from there, we break it down in smaller and smaller parts. So again, we repeat it as much as possible, and the final product is a hierarchical graph. And so again, what we want to do is convert our high-level graph, or low-level graph, to a high-level graph. And to do this, it's almost like doing that conversion from world space to node space, which is kind of a quantization step, right, is what we want to do. And that's the kind of same stuff we want to do. We want to represent our world in different stages, right? And that's what we're going to do. So we're actually going to perform the pathfinding problem. We're going to use the pathfinding problem multiple times, but we're going to do it at different levels. And what this is going to help us do is kind of move from one part of our world to the other, which is kind of neat. How about connections? So we have different groups. So here we can see that we have a group of nodes that are here. let's say we have a group and we have another group of nodes that are over here, another one over here. We want to get from our start node to our end node. That's the high level path. We know we're going to go from group 1 to group 2 to group 3. That's our, leaving our house, going to our car, driving to the airport, kind of thing. Big stuff, right? And then inside, we have our low-level stuff that's happening. Well, somewhere inside of our low-level stuff, there's an exit point. Maybe the exit from your house to go out the door, right? From your house to the car. What's that connection, kind of thing. Or maybe a better example would be from your house, you leave and you go to the bus stop. You leave your house. Maybe there's an inside of the house, outside of the house. And then from the outside of your house, go to the bus stop, whatever it's going to be. Or there might be multiple multiple points. Maybe the bus, maybe if you have access to both a car and a bus, then maybe the car would be maybe, far further, or maybe it's going to cost more gas or something else like that. There might be other reasons why there's two nodes out here. But example, you have a connection. This connection between two low-level nodes from inside of the groups allow you to traverse from one group to the other. That's what the example is. Okay, move between groups. And with those connections, you're going to have a connection cost. What's the connection cost between groups? And there's different ways of calculating the connection costs. One of them is the minimum distance method. Another one is the max-min distance. And the third one is the average minimum distance. So there's three different almost heuristics, other heuristics we're using to calculate the minimum, the cost that connects both groups together, okay? So the minimum distance, like it says, is a heuristic that uses the cheapest link between any nodes in those groups, right? And this makes sense because the pathfinding algorithm will try and find the shortest route between locations anyway. So the minimum distance is going to say, okay, what's the minimum, the shortest route, the shortest number, right? Is what it's going to try and find. And that's going to be the connection cost. So for example, if the node cost for the smallest number is 1, that's what's going to, the connection cost is what it's going to be, right? So going back to this thing. So let's suppose from here to here is a cost of 1, and there was other ones that are costs of 3, 4, 5. We only care about this lowest cost, and that's going to be the connection cost. That's the minimum distance, or the minimum distance one. The other one is the max-min distance. So there's two things you have to consider for max-min. The incoming link, right, as an example, and the outgoing link. The incoming link, so basically a path into your group, right? The minimum distance to any suitable outgoing link is calculated, right? And then the largest of the values that you find inside of of your group is going to be used for the outgoing link. So let's suppose I have values, going back to this thing. Let's say, for example, I have values that I have 1, 2, 3, 4 in terms of values. So the incoming link, let's say, would be, as an example, there might be an incoming link that's 1, but 4, because I have values of 1, 2, 3, and 4 in terms of distance, 4 would be the path cost to connect us, okay, as an example. So you might have whatever's going on inside the group, but from here to here, it's a cost of 4 because that's the largest value, whatever that is. And I'm using a cost of 4 as an arbitrary value right now. And let's say, for example, here, the largest cost between links is 7. Then the link between here and here, or here and here, they're both 7. So then you can try and find the shortest path between these things. And if you have multiple groups like this is just 3 groups that are linked together, right? As an example, with the end node, you might have a bunch of different groups linking together from this start node. Then you have to decide which of those, ways to go. Remember, these groupings can represent rooms. They can represent, larger objects like buildings. They can represent cities. They can represent whatever you want them to represent. Okay, so that's the max min. The last one is the average minimum distance, which is always generally a good choice. The reason why is the value in the middle of these extremes is what you use. So you're not going to use the most expensive distance, right? The highest one, and you're not going to use the minimum one. You're going to use something in the middle. And a lot of times that choice in the middle, if you have a lot of longer paths inside for some reason, or shorter paths, is going to give you a more reasonable amount, reasonable connection cost. And it's a lot better a lot of times than max min. But what you do is you average them. So for example, let's suppose I have 5 different nodes inside with 5 different connections. And I have, like we said before, I have 1, 2, 3, 4, 5. If I was to take the average, remember how average works? For those people who forgot, we can add all those up, add all the numbers. Let's say if I have a path cost of 1, 2, 3, 4, 5 for 5 different connections. 1 plus 2 plus 3 plus 4 plus 5. That's the different costs, right? And then we take that total path cost of 15 and divide it by 5. And you can see that the average cost is going to be 3. And that'll be your connection cost for the average, using the average minimum distance. Okay? And that's how it works. So again, we're just talking about connection costs. So that's cool, but there's some weird effects that happen. Actually, there's some weird effects that happen with A-star and pathfinding in general. And you're going to see that this week in lab when we get there, right? And it gives us an approximate solution like everything else, right? That's what it does. Just like any other heuristic, it's going to be performing depending on the circumstances, depending on what you throw at it. And that's why it's really great to stress test your assignment 2 as much as possible. And we'll talk about that. So again, at a high level, we might be able to find a route that's a shortcut, but sometimes that shortcut can't be found because of the stuff that's going on inside. All right. Let's talk about this in a bit. So here's an example. All right. So remember, the source of this approximation is the link cost, the cost between groups, right? We calculate when we turn the lowest level graph into a hierarchical graph. Okay. So because no single value can accurately represent all the possible routes through a group of nodes, they will be wrong some of the time. Just part of the way it is. So here's an example of some nodes. I'm just going to zoom in here to see this, right? Notice that there are these little room divisions, right? And these room divisions are the groupings. This is group 1, this is group 2, this is group 3, let's say, and this is group 4. Okay, so different groups in a room. And you want to find the shortest path between the start node and the end node. So the generated path works like this. Start from here and go from here and here, because you know what? You want to find the shortest path out from here when you're doing your route planning. You want to go from here to here, from this node here to this node here. Why? Because there's only 2 groups, group 1 and group 2. Here there are 3 groups, 1, 2, 3. So you wouldn't want to go this way because these count as hops. I want to have a path cost of 1, 2, 3, or I have a path cost of 1, 2. Hierarchical, right? So you know that you want to go from here, from this node, instead of going this way where there's multiple rooms, you want to go to this one, right? So this is the way it goes. So you go from a start node, cost 7, from 7 it goes from here, from this point it goes to 5, so there's 12, 13 to cross the path, because the minimum path cost, right, from here to here is 1. This is using the minimum method, right? That means the cost between nodes, the cost between groups is 1. Okay, so I'm going to go from here to here, and then keep going, and then 4, and then 8, and the total trip cost is 25. Whereas, if I went to an optimal path this way, even though I'm going with 1, 2, 3 hops to different groups, you can see that the path cost from here to here is 1, from here to here is 1, here to here is 1, let's say. So 1, 2, 3, 4, 5, 6, and then 3 is 9. So for a total 9. And why didn't it find this route? Because you only care about the ones from a hierarchical, a very high level. You only care about this stuff. Now, does it have to be this way? Hell no. You can use the, instead of using the minimum distance, you can use the mini-max distance, right, as an example. So what's the maximum distance? Well, they're both 1. That's what it is. They're both 1. And then, again, even mini-max or maxi-min is what it's called, is still the same. It's going to provide the same thing. What if I use the average minimum distance? So the average low minimum, right? So I go 1 plus 7, as an example, and plus 5. 1 plus 7 and 5. What if I did this one? And if I calculated that, I only have 3 nodes in there. Oh wait, there's also another node here we didn't take into account in this one. These paths are also important. We just didn't really put them together, right? But let's put some numbers here, and let's suppose this one and this one are both 5, right? And let's suppose this one and is also 7, and this one's let's say 6, and this one's 8, right? So you can see these ones are big. This is, let's say this one's 1. So if we calculate all those together, you'll get another number other than 1. So why do you care about that? Well, because now your connection costs are higher, right, as an example. And it could equate to a lower way of going this way, right? Again, you can't see with hierarchical pathfinding, you cannot see inside, the buildings, as an example, inside the groups, to figure out what the total cost is to get out. You don't know what that is because you're trying to figure out the path, the best path to get to the end node. Okay. Let's go out to the next examples. That's that one. That's where it's funny because, again, you'd think that this is the right path, but it wouldn't find that because of the number of rooms. How about in another situation where the end node's inside of this room? So here's the end node inside of here, right? And now it's only connected by 1 room away, right? So the right thing to do is go this way. But this is where maxi-min comes into play, right? Where the connection cost here is 10, right? Because of what we've calculated here, right? And the connection cost here is 1. Remember, inbound and outbound costs, right? So what ends up happening is, of course, it goes the other way around again. Right? So these are all pathological. And we say pathological because it doesn't make sense that the engine would make you go all the way around this way compared to going through here. But it's because of this path cost right here, right? This path cost looks like it's 10. This looks like it's 1. So it's going to go out here this way and make it the wrong decision again. Okay. So again, optimal path cost is 12, but the total path cost is 25. Okay. Any questions around hierarchical pathfinding and some advantages and challenges? Advantages for you. What about for you? Think about your tile map, right, that you're trying to do. So you have this idea, right, with your tiles, and you want to go from your start to your goal tile, right? And let's talk about some stuff that can block you with different kinds of heuristics. And I drew these heuristic numbers here because I'm using Manhattan distance, but we're going to just erase them, right? And we're going to calculate them again based on our paths for a second, okay? And we'll use both heuristics and just for the example. So I'm just going to wipe these out. And this is where you can bring up your Excel spreadsheet to try this out. Let's suppose at G, whereas the third column, we're going to have a wall that goes all the way down to the 5th row, right? So a wall that goes down here. Let's draw it by drawing it with black. There we go. There's our wall. And let's also, to draw this out, let's draw another block that goes this way from row number 8 all the way to about row 4. Let's draw another black mark right here like this. And to further complicate this, let us draw a wall that goes from in column 7. Let's go from row 6 to about row 9. All right, so that's the kind of the thing it's going to find, right? And furthermore, let's continue drawing a wall from this one, another 2 bricks like this one over here like this. This is the wall we're going to find, right? And one more, we're going to draw another kind of wall. So let's say from, row 11, right? From row 11, we're going to draw a block at row 11 and row 9, column 11, right? And let's make it so that it's actually here. If you can draw something that looks like this, okay? So here's some stuff, and let's talk about the shortest distance using Manhattan, okay? Remember the way Manhattan works, where you have your F is equal to your G plus H, where G is your tile cost and H is your heuristic, right? F is the total cost, right? So we don't care about G because let's suppose that all tiles cost the same. All we care about is the heuristic. What is the heuristic? Manhattan. Manhattan distance says that you're counting tiles, right? That's what it is. So how many tiles are there? And we're going to also wind in a top. We're going to take this order, top, right, bottom, left order, that we're going to wind this way. So we're going to go top, right, bottom, left when it comes to tie breaking, okay? So let's take a look at this. So what is the distance between this tile and the goal tile? How do we know that, right? Well, let's count tiles. So we're going to go 1, right? And again, if we're here, starting at the top, then I have to go either to the top or right. The right is cheaper, right? So we're going to go this way. So that's from here it's 1. Let's just count. 2, right? And we're going to go 3 and 4 because we're going to go down here. This is what Manhattan will probably do. Start up this way and go this way. And then it will go down to here and it'll be 6, right? To get to there, right? And now let's see about if I started here. It'd be from 1, 2, 3, 4 to get to there. So we clearly wouldn't do this path because this path is just better in this case than the other ones, right? Again, going down here is 1 distance, so we can go this way as well, right? So these two are the exact same, whereas this one, if I went to here, right, if we added more, this would be 4, this would be 5, 6. So this would be like path cost of 6 to get to here, whereas this one has a path cost of 4 to get to there, right? Okay, so we're going to keep calculating. Here's our start, and we can code the start like we did before with a green dot, and we'll make this one make it red, so we can see that clearly that's where it is. And let's keep going. So again, we're going to go 5, 6, 7, 8, because we're going to go across this way. We're not going to go up because we're going to find that going up is more expensive. But what about down here? Is down here cheaper than going up, right? Well, remember, we travel this way. If this way is 8, right, as an example, then what's the distance? And the way we calculate it is the total distance between on the difference in x's and the difference in y's. So if we were going to try and do it mechanically, we're just counting squares, right? That's what we're doing, but we're going to see the challenge. So again, what we would do is we say, okay, from here, from this one to here, how many x's do we have? So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the 14 across the x-axis, that's here, right? That's the difference in x's. And what about y's, right? And that's the absolute value added together. So 14 plus, that's to here, right? And then from here we go, 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. So 8 more. So 14 and 8 is 22, right? 14 and 8. So this is the x and this is the y count, right? And we put 22 again right here, 22. All right, so what about here? Well, we're one lower, right? So that's 21. And this would obviously be 23. And because this is farther away, this would be 24. So it would be 24, 23, 22, 21, 20, right? And then we come here to 19. You can calculate this yourself. 18, 17, 16, 15. Okay, so we're there. Now it's also 15 this way. This is the decision point. And this is also 16 this way, and there's also 17 this way, and there's also 18 this way, right? Because you can go either one. Same, right? All right, cool, 15. There's 14, right? And so now you're here, and this would clearly be 16 because this is higher up, right? Higher up means farther away, and so this is more expensive. And notice that these numbers, right, we can draw them in diagonal because the numbers here are always 16 as you go further up. This is how you see it. It kind of is a diamond pattern that you'll see later on, okay? And same thing with these numbers. So this will be 15 up here, okay? And I'm not going to fill in this whole spot, but you can see that this is clearly not the way to go. It's not going to go up that way because from here, we can go 15, which is this way. This is a block, so this is impassable. And then what's the cost of this one? 13. So we can go 15, a block, which is infinite, 15, infinite, 13, 15. Oh, which one? It's going to go here, 13. So 12, 11, and now it's going to go across 10, 9, 8, 7, 6, 5, 4, 3, 2, and then right here, right? That's how it's going to travel. And we kind of calculated this is slightly wrong because this should be 22, and the other one should be the other way. But you get the point. It goes in this route. It goes from here. This is actually 21, and this is 20. I just calculated wrong. So 21, 20. You can pull it down with Excel. You can do one of these, right? You can pull it down to calculate the costs, and then you can see that this one will be a possible route, and this one will also be a possible route. all right, because this is the way it would take. Hopefully you guys get what I'm doing and why I changed the numbers, because I made a mistake. All right, so 15 to 14, this one would be 15, not 16. So these ones all in a diagonal, these ones would all be the same values, just to show you this, okay? And this one would be 14, 14. Okay, so that's how it works. So what about, why would I go this way, tiebreaker? Because when I'm here, I can go either this way or this way. They're both the same cost, right? They are. They're both the same cost. But I'm going to go this way because we've decided that going this way is actually, we're winding in a right winding order, and this one comes before this one in our array. So we're going to go this way. So let's mark this off. So we're going to use this just color. We'll make it green. For this one, just a different green color, so you can see what would be done with Manhattan when we have some kind of obstacle like this. All right, so we're going to kind of map it here, and it goes to there. And by the way, the numbers are wrong because this goes 9, 11, 15, 14, 13, 12, 11, 10, right? And this will be 9. But for the most part, it's exactly the same as what we've mapped out, right? Just the path is the same, right? But what it's going to do. And this is based on the obstacle that we have in place here. Okay, now this is Manhattan. What does Euclidean do? Okay, so Euclidean, what it does is it goes, okay, what's the distance as the crow flies from this point to this point? From this point to this point. And what it does is it takes the difference in x's, right, 14, and the difference in y's, 8, adding them together to produce a number, so 22, and then you take the square root. So square root. So what is that? So you say, I want to take this squared, right? So take the difference in x's, right? And you want to get the power of that. So I want to say, I want to get the power in Excel. You want to use the power of this to 2, right? Whatever that is. Plus, I want to get the power, you can use the formula, of this to 2, right? And I want to take all of that and I want to put it inside of a square root. So then take that whole thing, I want to use a square root and surround all of this with that. So now we get a value of 16, roughly. And by the way, the value is not 16, it's actually much longer, 16.125, but we can see that we probably want only one significant digit. So if we're going to do or Euclidean, from here it's 16.125. From here we change the values, right? So it's not 14, but it's actually 13. Look, I'll change the values every single time. So let's do that. So it's 13 across. So it's 13 and 8. So it's 15.2. So here it's 15.2. We're just redoing the numbers, 15.2, right? And we'll just make it so that it is wider so we can see them slightly. There's 15.2. And then what about up here? So that from there, it's up one higher, so that's 13 and 9, right? So that's 15.18. 15.8, sorry. 15.8 is more expensive than 15.2. And what about over there? So this one there is, again, it's one more on this one, on the x-axis, and also higher, so it's 16.6. So this is clearly not a good deal to go this way, all right, 16.6, right? And if we just make it the same size, again, it doesn't matter, we'll just do that. So this is 40 pixels. We'll go back to 40 pixels again, just to show you that. I wanted to show you that there's more stuff going on here. So this is 17, 16, 15. This is what it's going to do, right? So here is, again, it's, we started off at different numbers. Again, the way I figured this out, for those people who are confused, right? No, obstacles and walls are the same. They're impassable, right? So that's how it's going to be. So again, the way you count it is how many on the x. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And you would have from here 1, 2, 3, 4, 5, 6, 7, 8. So 14 and 8. So that would be the way you calculate that. The first thing, which would be this one. That's that block. So what about if I'm 1 over? So that's 13 and 8, right? And then what if I'm not going to go there? So what about, and I can't go there. This is impassable. So what's here? So this is 13 and 7. So this is clearly going to be 14.7, right? And this is, what's the next one? 13.7, so it's going to be 6, So this is 14.3. All it's going to be is just different numbers. And then from what about here? So from here is, this is 5 as we're going down, 13.9. And the other numbers are going to be higher, clearly. Now, here's where we can become different. Okay, so what's this one? So this is on the x-axis, it goes to 12. That one stays the same. That's 13. Okay, and what about this one? This one here. So this one, to go here, is, again, we're going to go down on the y, but keep the same on the x. So go back to 13, but then we're going to go down on the y, right? So that's going to be this one. So again, 13.6. So again, depending on which one you want to go to, this is 13, this is 13.6. I'm going to go this way. And I'm going to march across like this until it's cheaper to go the other way around. And I'm just calculating for Euclidean distance. That's what I'm doing here. All right. So again, 13.4. I'm going to step it back. So it's 5, 13 and 5. And then we're going to go across. So that means it's going to be 12 and 5, 13. And then it's going to be 11 and 5, 12. This will be 12. Right. And then it'll be 10 and 5. Right. 11.1. And this is the distance, Euclidean distance, not the number of tiles so far, okay? Now what about when we get to here? This is where it's going to be interesting. 11 and 1, and then we're going to go to here, which is, 9 and 4, right? So that's 10. And which way would I go? Would I go up? Well, that's clearly longer than going down because I'm going to have to go in the same thing we just got. I'm going to go up because I'm going to increase my y to 6. So that is not 10.8. Okay, and what about if I go down? If I go down to, on the y-axis, if I go down to 4, right? So if I go down to 4, that's going to be 9.8, so it's going to be here, 9.8. Can't go to the right because of my wall. My wall will not allow me to go right, so now it's going to be 3, right? Which is 9.4. 2, which is be my 9.2. 1, which is going to be 9.0. Now, here's interesting. I'm here at 9.0, and what do I go? Do I go down more or do I go to the right? Well, because we're right winding, we're going to make the decision here depending on what it is. So what is this one? This will be 0. We'll go back up. This is exactly 9 here. And again, it's not sure. It's not really 999. It's 9 point whatever, right? And then let's go back up to this here, and I'm going to go across to this 10. So 8 and 8.06. Notice that it favors Euclidean distance, also favors this method when I come to here. So I'm going to keep going, keep going, keep going, keep going, marching across, but the number is different until I get to about here. And this is where Euclidean distance will try and calculate maybe a different number. So what is the x? It's only 1 away. And what is the y? It's only 1 away. So whether I'm here or here, it doesn't really matter. It's here when I'm from this position, I'm at x is 1, and then y is 1, right? So they're both 1.4. This would be a 1.4. Now what about from here? If x is 0, right, and y is 1, it's 1, where y is 0 and x and 1 is 1 and 1. So these would be all 1s, which means I would still do this. So this is the exact same path. Even though we're using 2 different heuristics, it doesn't really matter in this case. Does that make sense? And I've done this mapping exercise with you before, and maybe in class. And guys, I'm running a little bit overtime today, but I'd like you to stick around just a little longer for me to finish. So why did I show you all this? Because I wanted to talk about the different methods that we use. But notice that the green path is the exact same, whether we're using one heuristic or another. But here's an opportunity for us. Here's an opportunity for us. What if I was going to use hierarchical pathfinding, right? And I divided this area into different parts. So example, I wanted to say that this area here is the end of this one. This is the beginning of one. And I can break this area down into different pieces, right? And where this one is its own little piece. So I have a kind of an entrance and exit there, and maybe there's an exit and enter there. So there's be a room here, and maybe we'll break this down into a room here, right? So you can go that way, and a room up here. So there's a room, 1, 2, 3, 4, and maybe we'll make it so that there's another area here. Again, you can basically chunk it off in the way you want, right? So, okay, and let's just break off this room up here like this. So there's a bigger room. So now that we're breaking these off into chunks, high level, I want to go from this group to this group over here, right? This is where I want to go to. And by the way, you can even break it down even further if you want and make it so that it's like this, right? It's up to you, right? But these are almost like a nav mesh, right? In some ways, right? So here's one group, here's another group, here's another group, another group. And let's say, for example, I want to go from here to there. Well, if I travel in groups, I go 1, 2, 3, or I can go, right? 1, 2, 3. Either way looks okay in terms of pathfinding. Right now, it's a matter of what the values are inside this room compared to this room, right? And it really depends on how these rooms are drawn. So example would be, let's get rid of some of these numbers, just so that you can see what I'm talking about. In another more complicated scenario, where let's just get rid of all these paths so you can see what I'm saying, right? So let's suppose that these are the rooms that I want to define. So now, what about, how do I do pathfinding, hierarchical pathfinding here in a different way? So break that down, good. And let's make these an actual, you can draw it yourself. Make it so that there's only a doorway out, and here's a doorway this way, and we'll make a wall that goes here. So you can see that there's clearly a wall that way, and we'll make it so that there is a wall that goes like this, and we'll get rid of that one. Oops. Get rid of that one to make it white as an example, and make it so that there's an entrance there to that that part right there, which will be the same yellow one that we've been using the whole time. And over here, we'll make it so that there is another doorway that's probably over here, let's say. So we'll make this all black, and we'll make this black. There we go. All right, so that's the doorway there, and there. Now this makes perfect sense compared to what we had before in breaking this down, because how would you find the shortest path now where you don't know the cost to go through these doors, right? And that's what hierarchical pathfinding can, yes, Aiden, no problem. And that's what hierarchical pathfinding will allow us to do. It'll allow us to figure out the connection costs, the door cost, going through the door costs from all these little pieces, right? As an example. And sometimes there'll be, we can clearly see that, for example, the distance normally would be better this way, right? We might see that this is a shortcut, but our algorithm might take us this way, because depending on how it works. And the reason why is because this would be a node. So you'd have a node to go here. This would be almost like a preliminary target. So this would be a preliminary target. We'd have two targets, this one and this one. What's closer? Which one's closer, here or here? Well, clearly this one's closer. Okay, cool. And what's closer, from here to here, right? Or from here to here? Well, this one's closer. So maybe it's going to go this way, depending on the algorithm, and it might mess you up and go up here and go down that way, as opposed to going all the way here, right? So that the thing is, and what you're trying to do is subdivide your world into something that makes sense, but it can become complex, is what the answer is. All right, so that's a little bit of hierarchical pathfinding and some strange effects of it and how I can mess this up. Last topic is heuristics for grids. We talked about a bunch of stuff. What I've put on here for you is the A-star algorithm one more time so you guys can see it. So it's here in a very short kind of way of doing things. And what I want to talk about is just really two other quick heuristics, and we're done. One of them is called the diagonal distance, right? So it's really like Manhattan distance, but what you want to do is take the maximum of absolute values of differences in the x and the goal's x and y coordinates. So it's like you take the difference in x's and the difference in y's, and then what you try and do is what is the maximum value, and that is your estimate. So And it says, if you go back to this little, on page 27, it says, on a square grid that allows 4 directions of movement, use Manhattan distance, right? On a square grid that allows 8 directions of movement, use diagonal distance. On a square grid that allows any direction of movement, you might or might not want to use Euclidean distance. So diagonal distance may not be good for us, as an example, right? It may not be good for us, but what it can do for us is when we go back to our little grid, as an example, if I want to try and calculate the maximum, right, like we did before, then we add up all these numbers, and the number from here to here, because x is max compared to y, is always 14. So this is like, that's the number. It's going to be 14. This is going to be 13, right? This is still going to be 13, but it's now what happens when you come to this? Well, it doesn't make sense to use diagonal because this and this are both 13. Why? Because the difference between here and here is the same as this, and it's less than this to this. that's what it's calculating, right? So it's like 13, 13. This one's more because it's farther away. So this is like 14. So you wouldn't want to go here, right? Because it's farther away. And so you want to stay with these ones until, let's say you can go through the door, let's just say, then this would be like 12, or, as an example, 11, 10, 9. And now you get into a little bit of differences where this one is equal to this one. Because remember how we did it in our thing? We use a right winding order where we go top, right, bottom, left. And so this one would be 8, but this one would would also be 9. So this would be 9, and this would be 9. And now we're going to use this one because we're going to go up because we're going to tie break on the way up. So we're going to go this way. And we're going to go 8. This is what it would do. This is what diagonal distance would do. 6, 5, 4, 6. Sorry, this is 6, 7. These are all 7. 7, 7, 7. This will be 6. 5, 4, 3, 2, 1, 0, right? Because we're on the same. And now we're going to start using the other one. So now we're going to go down this way. So this is, now the difference is it's higher on the other way around, right? So when it comes to lower, when it comes to these ones, notice that the difference between here, there's going to come a point where, if I just draw the diagonal, right, that there is going to be the same number between here and here. Right, so this is 7 either way. 7 either way. If I go down or if I go up, it doesn't matter. 7. But what about when I come to here? Well, now it's going to be, which one is shorter? Is 6 shorter, or is 7 is the maximum? Right, so it's going to be this one, this way. So when I come to here, instead of going around this way, it's going to go down here. So it's going to go 5, 5 like this, and it's going to basically hug this lower value. If it can go through the door, by the way, it will. It'll keep going down this way. Because that's the way it's going to go. And then when it comes to here to a block, now this is where it becomes funky for pathfinding algorithms. I got to talk about this because remember, it's going to find one or more possible paths. It's going to come here and it's going to say, "Ooh, marching backwards is more expensive than going back up. Either I'm going to stop because it's more expensive going this way, and I'm going to pause and go try this way." So it's going to try, kind of going this way a little bit, and then it's going to go to whatever the distance is this way now, right? So it's 1, 2, 3, 4, 5, 6. So it's going to be like 6 this way, because that's the new max, right? So 6, as an example, and it's going to keep marching around across this way because all these ones are lower. So 5, 4, right? And it's going to keep going 4, 4 because that's still lower, right? Until it comes to here. And now what is it going to do? Because I can't go down any lower, it's got to figure out a way if you can go this way or this way, and that's why you're going to have different paths. So that's what diagonal distance does. It's a little bit different than Manhattan distance. And that's what it does. It uses the absolute value. So it only counts the longest route between this one or this one. Kind of a neat thing to do. And another way of looking at it is this way, and what it does, it kind of steps down, but if you're allowed to travel diagonally, this is where it works great. If you're only allowed to travel in 4 directions, don't use, because you saw the problems, right? If you can't go diagonal, then you want to use Manhattan. Okay, so there's also another one called best first search, right? And best first search is a greedy algorithm that tries to find, that really tries to evaluate ahead of its time, its successor. So it looks at its first successor, and tries to find out, if there's a better way of going. It still maintains two lists, just like A-star Pathfinder does. But let's take a look. So here I have these values here. I have 3, 6, and 5. Let's suppose these are the nodes, right? And I put A, and then I order it in terms of priority. So it's 3, 5, and 6. So it goes A, C, and B. That's in my new array. That's how best first search works, right? So I'm going to go A first. I'm going to look at A, and I say, do I have any successors that are not leaf nodes and that are the goal node? And the answer is both of these are 2 leaf nodes. So we're going to just chop away A. So A is no good anymore. We're going to say that A is no good, because we're going to say that this is no good because these 2 are leaf nodes, right? Okay, let's go to C now. We're going to ignore B because B had a higher value than C. Let's go to C. Does C have a successor node that is not a leaf node and that's not the goal node? Yes, it does. Let's add that in, 7. Okay, good. Now let's go to H. Still, by the way, B is on there. We haven't explored B yet. Let's go to H, and it's going to say, okay, H, is there any, does I have at least a node that's not a leaf node? So this is no good, but hey, this is the goal. So this is the goal node. This is where we want to go, right? So guess what? That's the shortest path. This is what the path is going to find. And it's going to find that just like that, right? Whereas in other scenarios, I might explore this one first. If I was to do something like A-star, I might do this first, right? Because that I might explore. Then I would explore this path, right? So both paths. Then I would go back here and then start exploring this one, just like kind of like what I did. But best first search, what it does is it ignores, it almost like prunes this part of the tree, because it's like, well, this is more cost, right? So, and again, you can explore it in different ways. I know I lost some of you, but hopefully there'll be other people that'll stick around. I know you guys have to go. But you can explore it in different ways. And the last thing I want to show you with this before we get into our last thing is, what if there was a connection that goes from here to here? And let's say this connection was really small, so like something like 3, right? Now, best first search works in a binary tree type algorithm or a tree type algorithm. And this connection between nodes would be not possible normally. Okay, but let's suppose there is. Let's suppose there's a shortcut to get this way. So it would go and look at these 3 paths. It would look at this one first because it would say, hey, we've tried this out, but no, we're not even going to go there because the these ones here are leaf nodes, so we don't care about this path. They're not going to go, and it's not the I node, right? And what about this one over here? Well, we wouldn't check this first. We would check this one first because we definitely have a path here that goes here and here. But now we have 3, 5, and 6. 3 is not a leaf. Maybe it leads back the other way, as an example. But this one is the goal node, and this is the shortest path, right? But we're also going to try and go back up and go, okay, cool. What about here? And it's going to go, okay, here. Well, this is a leaf, so we're not going to go this way, but this is a viable path. And is this shorter? No, it's not, because I'm adding 14 and 6 is 20, and I'm already got 23, and then this is 22, so this is clearly a shorter path, right? Or this is 10 and 7. This is 17, and here we've already got 20, so it's not even going to go here. It's not even going to connect because this one is already longer than one we found, and then it's going to stop. Okay, so best first search is interesting. It's a different way of doing things than way of doing things than A-star, and it's an alternative option for you guys. All right, so we talked about a bunch of stuff, hierarchical pathfinding. We talked about, kind of optimizations that we can make as well. And now what I'm going to talk about is the last part, which is what we're doing for lab this week. So this week we're doing find shortest path, right? As an example, we're going to display the path list in the nodes as well as spawn objects. What we're going to do is create a random obstacle in our grid, random obstacles that we're going to put there, and then see if we can stress test our algorithm so it can find the shortest path or have a termination condition to stop pathfinding. That's what we need to do. Okay. Any questions around the stuff we talked about today? So we introduced assignment 3 and 4, and we also talked about hierarchical pathfinding as well as some additional heuristics. Okay, if you want to stick around, Rakib. All right, guys, if there's no other questions, then that's what's happening this week. Hopefully that was okay, but we introduced a couple of additional things. Again, please make sure you use something like this when it comes to your testing. Remember, you can always reset it. This is what I wanted to say, which is, take it back to its original thing and try and map out, try and map out your world and move the stuff around to see if you can if the algorithm is spitting out the right information for you, and does it do what it's supposed to do. Try it out, put some obstacles in to try and foil it. You can do it manually or you can do it procedurally when you do your assignment too. And things that would foil stuff are weird cases. All right, weird cases. So what I mean by that is if you had a weird case like this. All right, so if you had a weird case where you had a wall that went this way, okay? And it's clear that down here is closer than here or here. What is it going to do when it gets to this point, right? That's a weird case, right? And does it go this way or does it go this way? Can't go back up because remember, these are all been marked as this one here and this one here has been part of the closed list because it marched down here and this way, right? So the only thing it can do is go this way. So it's going to march this way across back this way because there is no path up there, right? The other way that could happen, depending on your algorithm, right, is when it comes to here, right, is this way cheaper than this way? If this way is cheaper, it's going to go march back up here. And it's going to find that I've already been here. So it might do something weird like march across this way, right? Until it finds either one, like it might go like this, circle around, come back down. And because this might be more expensive than down here, it might go do something like this and do this kind of fill pattern until it finds, that it goes across. It might go right across to here if you're using Manhattan, right? And then down this way. That might be something it does, right? When it does that kind of stuff, it gets foiled by these kind of weird scenarios. So check it out. See what yours does. Does it get foiled up? Does it keep on, going around and around in circles, that kind of stuff, or does it stop? Right, you must have a stopping criteria. All right, that's really it. I'm going to stop recording now, and I know we're way over time, and I'll see you guys on Thursday. I'll take questions for the people that are here. I've got a couple of people that have asked me some questions and people that I meet around, so I'll stick around for those people. For the rest of you, thank you so much for sticking around. And yes, Aiden. And I'll see you guys all on Thursday. Thank you.